Right. So this is week. Oh, this is still week 1. So this is our week 1, Thursday. So the agenda is on unsymmetric pure bending. So if you were to refer to your course textbook, it'll be on chapter 4.13, and I hope some of you have downloaded the course textbook. Okay, it's the one that is by Beer and Johnson. So after this lecture today, I'm really ambitious. Okay, I want you all to be able to. I will make sure that you recap through this lecture the basic theory of pure bending. So what is the similarity between simply supported beam and cantilever beam? So sometimes when we analyze structure that's simply supported, right, we also can assume it to be a cantilever beam. There's something similar about it. And then we'll look into the difference between symmetrical and unsymmetrical bending. So from 2P04, you have covered a lot on, in fact, most of them is on symmetrical bending from 2P. I'm going to do unsymmetrical, and I'll show you what is the difference. And then we are going to work on to example problem. So I have uploaded a figure on Avenue to Learn. Okay, Avenue to Learn. So go to Avenue to Learn and download the figure. It's on the lecture section, so it's just an image. So the image will look something like, where is my image now? So the image will look something like this. Okay, so this is what we're going to do our problem set from. Right. So let's quickly recap. I'm going to assume that you all forget pure bending. Okay, I know some of you have taken 2P quite a long time ago. So I'm going to make the assumption. And in this lecture, I will teach you some analysis skill that I've learned by solving a lot of problems on pure bending. Okay. So let's look at pure bending. So now if we were to have a cantilever beam, a simply supported beam. So this is our simply supported beam. And one end, we had it as a pin. The other end, we have it as a roller. And over here, I'll call my point A. This will be my point B, somewhere in between. And this is my point C. And then we have a load applying at the center, exactly at the center. And this load is what we call our P. And based on distance, the distance from here to here is equal to L over 2. Likewise, the distance from here to here is equal to L over 2. Okay, so if we were to draw our transformation, this is our X direction, Y direction. Over here, this is our rotation about our Z direction. So from here, if we were to construct free body diagram, or we want to look at the reaction force, we know there's a reaction force over here, and this is your AY. And then you have a reaction force over here at CY. Why you have reaction force over at point A? Because Y displacement is equal to 0. At point C, Y displacement is also equal to 0. So if you restrict motion, you will have a reaction, which is your force. Okay. Whereas over here, from how it's supported, X in X direction is equal to 0, because on point C, we have a roller, X direction is not equal to 0. So if you are to complete a free body diagram, we should in fact draw an arrow over here to say that this is AX. But we know from this diagram over here, there is no X component, so we say that AX is in fact equal to 0. Okay. So now, in pure bending, like what you can see over here, okay, where the structure is supported and you have a load in the center, we can identify when we can find out the stress in the x direction, okay, is equal to mz over izz multiplied by y, and then you will in general you will have a negative sign in front of this formula. Okay, so this is a formula that we will generally use to find the stresses in the x direction. Okay, so stress x, so let me identify. So stress x is this normal stress in the x direction, and then you will have mz. Okay, so the applied moment in the z direction, the izz is the second moment of area about the z direction, or sorry, about the z axis, and y, you can see over here, is the y distance measured from the neutral axis. Okay, so in terms of units, this is in Pascal. Okay, or if we are in imperial, this is pounds per square inch, and then the moment is in Newton meter. Over here is in pound inch. Second moment of area is meter to power 4 in imperial, inch power 4. Distance likewise. Only once is in meter. Now, a lot of questions been asked about what do we mean by second moment of area. Okay, so second moment of area is basically resistance to bending. If someone were to ask you, what do you mean by second moment of area? So for this formula over here is very specific, is basically the resistance to bending. Okay. Now, an interesting feature over here is before I go, I'm going to ask you guys a question. Anyone could answer. Why negative? Anyone? Can anyone tell me why are we so frustrated with this equation that we have to put a minus sign? Anyone, please? I got dead silence. Are you all still there?
When it elongates in one direction, it gets smaller in the orthogonal direction.
Say it again.
When a beam deforms and elongates in one direction, it gets smaller in the other.
Okay, so that's partially right. That's a good attempt. So I'm going to write to you or show you why they are so frustrated with this minus sign. Okay, so the next thing that I want to draw over here is we like to sketch out the deformation pattern. Okay, so let's look at the deformation pattern. Okay, let's look at the deformation pattern. So if I were to sketch now how the structure will deform, okay, the structure will tend to deform this way. Yeah. Yep, the structure will tend to deform this way. Okay. So this is the deformation pattern because we have the load at the center, and then we have our load over here applied P, and then we have our usual point A and point C, and I'm going to use in green. Okay. This is our neutral axis. Okay, this is our neutral axis. So as you can see from here, right, and I'm gonna address 2 points. We're gonna address 2 points. So the top point over here, or the top over here, we're going to call it alpha, and the one below over here, we're going to call beta. Okay, alpha and beta. And at this point over here, we also call this location over here our point B. So point B has point B alpha, which is at the top, point B beta, which is at the bottom, and then we have our transformation X, Y, and then rotation about Z. So as you know, alpha will go through what? Like how does one of you answer? The distance has been reduced. So we know that this is the top part will be under compression, right? And then the bottom part at the one with the beta, this will be under what? Tension. Okay. So at the neutral axis, the stress, okay, the neutral axis, the stress in the x direction is equal to what? 0. So we are calculating stress in the x direction for this case. Okay. So now the interesting thing is, why is it minus? Okay, why the minus? So if we were to put a point down here, this point will be known as the center of curvature. So if that is the center of the curvature, the distance over here in terms of y will always be positive, moving away from the neutral axis, away from the neutral axis. Away from the neutral axis, away from the center of curvature. Y will be equal to what? Y will be equal to negative. Okay. So for this fact, what we see now, if we write stress X, okay, we want to find stress X at point alpha. And we know for this case, Y is equal to what? Y is what? Positive. So therefore, stress X of point alpha is equal to minus mz over izz multiplied by positive what? Y. Okay. So hold on. So multiply by positive y. So because the y is positive, the outcome is that this equation over here, the magnitude is what? Or not the magnitude, the vector will be what? Negative, showing that it's under what? Compression. Right? So if we were to find stress X at point beta, right? Now the y value now, because the beta point from the neutral axis is going away from the center of curvature. So what we have now down here, y is equal to a negative. So therefore, stress X beta is equal to minus mz multiplied by minus y now, right, over izz. So when that is the case, the outcome from here is this whole equation over here, minus times minus will be what? Positive. So that is why we have what? tensile. Okay, so that is why any textbooks that you see, it will highly enforce on this negative side. But there's another way that we can view